Hi, everyone. My name is Arvind. I guess I know most people in the room, and for people watching online, my bio is going to be right there, so let's dispense with the introduction. But perhaps the one bit of information about me that's relevant to this talk is that I'm a computer scientist, and this is joint work with Solon Barocas, who's in the back there. And the one bit of information there is that he's a technology ethics scholar and not a computer scientist. The difference between those perspectives, I think, is going to inform a lot of what I want to say today. So what is algorithmic society? What are we talking about here? The starting point for this whole discussion is the fact that as software governs more and more of our lives and more systems out there, a lot of people have been very concerned about the fact that everything from behavioral ads to, let's say, jobs and insurance and so on, and on the other extreme, even the global financial system is increasingly being run by algorithms, so to speak, and people are very concerned about this. They're concerned that these algorithms are inscrutable, they're not very transparent, we don't know much about the people running them. They're very concerned that these algorithms are very hungry for our personal data, and so they're concerned about the privacy consequences. They're concerned about the social impact of these algorithms, let's say any disparate impact they might have on different social groups of people. So that's the sort of the social question that I want to look at today, but I want to look at it from a computer science lens. How did technology develop to this point, the historical accidents that led up here, as well as how we should respond to this, and how in particular what should the technological response to this look like. So before I go too much further, I want to clear up what I think has been a giant terminological confusion between different uses of the word algorithm, between two different groups. One group is obviously computer scientists and technologists, and to a computer scientist, I think most of you in the room at least are computer scientists, and I don't need to tell you that an algorithm is basically a well-defined mechanical procedure, right? But for a lot of other groups of people who've been very interested in the impacts of algorithms, and I'm sort of using the umbrella term regulator here in a very, very broad sense of the term, but what I really mean encompasses many groups of people. Social scientists, technology ethics scholars, legal scholars, actual regulators, of course, press. So any other groups that I've left out? Yeah, yeah. Oh, stand on this side. Right. So, thanks. For all of these groups of people, it's not this sense of the term algorithm that's really causing a lot of the concerns that I just described. Instead, it's the aspect that algorithms lead to automated decision making. And I think decision making is the key part here. There have been, of course, a spectrum of concerns that have been expressed, and I'm simplifying a little bit when I say automated decision making, and that's really at the core of it. That's at the core of what people are talking about in the two different conferences here, basically on the theme of regulating algorithms. Algorithms and accountability was one, governing algorithms was another a couple of years ago, and Solon actually co-organized that. Both of these were at NYU, by the way. So, two different workshops on governing algorithms just from the same institution. Just goes to show that there are a lot of these going on around the country, around the world. There's been an explosion of interest in talking about what is the impact of algorithms. That's what people mean, for example, in Frank Pasquale's book, The Black Box Society. That's what people mean over here in Kevin Slavin's TED Talk, How Algorithms Shape the World. So already you can see a little bit of a tension between well-defined mechanical procedure on the one hand and decision-making on the other, because as computer scientists, the way we teach our undergrads about algorithms is to ask them to think of a recipe, right, as a good analogy. And the key thing about a recipe is that it sort of takes the decision-making out of cooking, and you can follow that as a mechanistic procedure. And so the way computer scientists conceptualize it is already somewhat different. But the differences are actually deeper than that. One way to think about the difference is that these two groups of people are looking at algorithms at very different levels of abstraction. For example, in response to this TED Talk, the consensus among the computer scientists, at least, that I talked to, was that it was sort of full of hyperbole. And maybe there is some truth to that, but also this confusion came out of just a simple linguistic difference between the way in which algorithms are being used over here and the way that, in which they're being used over here. So when this group of people, and I know I'm simplifying a little bit when I say this group of people, it's not one group of people, it's many different groups of people who share some similar concerns. When they make statements like algorithms are inevitably imbued with politics and cannot be neutral, right? The sort of statement, it's a deep statement and it has a lot of truth to it. On the other hand, when a technologist hears that statement, they think about their prototypical example of quicksort, and they conclude that this group of people has gone crazy and completely ignore them and stop paying attention. So that's a little bit of what's going on right now. There's, and this has impeded communication, but I want to emphasize that there are these two different senses. And I'm going to be talking about this sense of the word algorithm, but I am going to be taking a computer science perspective on that sense of the word algorithm. And to make that difference even more clear, let me give you one concrete example of how these two groups of people talk about the term Google search algorithm. Right. So to a computer scientist talking about the Google search algorithm, many of you might know the name for it. PageRank, exactly. And the mathematical formula describing PageRank can in fact be described in an extremely simple fashion. It's just a iterative weight update procedure. Many of you may have seen this in computer science classes. To compute the PageRank of a node in the web graph, what you do is you look at the PageRank of its neighboring nodes that you've already computed, and you sort of take a weighted average of that, and you update the weight of the current node, and you simply iterate this procedure until it converges. You need a damping factor to ensure convergence, but that's it. That's all of it. And you might see, that it's the opposite of inscrutability. It's something really, really straightforward. And in fact, some of you might know that PageRank is just a tweak on something even older called eigenvector centrality that's been used not just in computer science, but even in social science. And that's something even simpler. All you're doing here, just this equation with 4 terms, and it expresses eigenvector centrality. All you're doing here is you're representing the web graph as an adjacency matrix, and you're computing the eigenvector of that matrix, and that represents the PageRank vector of the web graph. That's it. It's that simple, right? Anybody with an understanding of linear algebra can immediately get it, and they can implement it, no problem. It's very, very straightforward. However, it should be equally clear that this is not what people are talking about when there are lawsuits about the impact of Google's search algorithm on Yelp and competitors. This is not what people are talking about when the European Union, as you may have seen in the news today, wants Google to share their algorithm. This is, of course, not what they're talking about, right? Very, very different. There's a huge difference between this, what computer scientists think of as the algorithm, and they would think of everything else surrounding it as the engineering, of course, and treat that as somewhat boring and not even teach it in classes. But of course, that's where all of the relevant factors in practice are, and that's what people are talking about when they're talking about the economic and social impact of Google's search algorithm. And that's why there's a team of hundreds of engineers that have been continually maintaining it well over a decade, and why Google's updates to its algorithm are a huge deal in the SEO community. None of that would make sense if this is what we were talking about, even though that's what we teach in computer science classes, right? So huge, stark difference. I wanted to be very clear about that. Different levels of abstraction. So I'm going to be talking about this sense of the word algorithm. Yeah. Okay. So one thing I want to do to establish this whole historical accident line of thought is I kind of want to draw a line between this, which is a picture of the famous 1954 Dartmouth AI conference, which really started the notion of AI and research on artificial intelligence. I want to draw a line between that and this, which is Jeff Hammerbacher's quote, which goes, "The best minds of my generation are thinking about how to make people click ads." Right. So what's the connection between these two? What Hammerbacher here is talking about is the notion that machine learning today, what he means by best minds of today's generation is all the scientists working on machine learning, which we acknowledge as sort of the cutting edge of artificial intelligence. Where it's being used, perhaps more than anything else, is in online behavioral targeting and things like that. So I want to draw that intellectual lineage between the founding of AI to where we ended up here, and use that to talk about how machine learning is driving algorithmic society. And I'm going to take, it's going to be a short, but nevertheless somewhat, I'm going to be poking fun at the history of AI a little bit. And I want to be very clear that I'm not in any way criticizing the people involved. They were, towering giants of their generation. They were responsible for a lot of the foundational work, not just on AI, but also computer science in general. But it really goes to show that even with incredibly smart people, entire fields of research can meander in a direction that ultimately turns out to be unproductive before, as in the case of AI, finding its footing ultimately in what we call today as machine learning. And the tidbit that I want to start with is this is just unbelievable. Marvin Minsky apparently hired an undergrad for a summer to solve, quote unquote, the vision problem. right? And now we have entire departments devoted to it, hundreds of PhDs being churned out, and yet we're making small amounts of progress on the vision problem. So this shows, not only did the pioneers of AI greatly misestimate, if you will, how hard the problem was going to be, but also which parts of the problem were hard and which parts of the problem were easy. And this picture really nicely illustrates that. It turned out that what they thought was the hard problem, which was teaching a computer to play chess. And in fact, teaching a computer to beat the world champion at chess turned out to be a far easier problem than the problem of building a robot that can recognize the pieces on the chessboard and move those pieces accordingly, right? So that turned out to be a far harder problem, which we haven't still fully solved today, but beating the world champion at chess was easy. Right? So yeah, it didn't have the scope of the problem right. It didn't figure out which parts of the problem were hard and which parts were easy. But it was more than that. It turned out that even after we could beat the world champion at chess, that whole line of research didn't have much of an impact on the rest of AI. It's a little bit of an island game-playing research within AI, because it turns out that that kind of intelligence doesn't generalize to other kinds of intelligence. But the kind of intelligence you need to actually move pieces on the chessboard, that in fact generalizes very well to even natural language and other things. And I'm going to say a little bit more about that. So just continuing with that history a little bit, the 50s were the birth of what we call AI today. The 60s, it was the great obsession during that time was symbolic reasoning. I think Prolog was born during that time, and perhaps Lisp also matured during that time. I'm not claiming to have the exact years of everything exactly right, but this is just to trace the general flow of ideas in artificial intelligence. And the idea was that you could encode a lot of the intelligence into your programming language itself, so that the programmer could express their tasks in a bit of a higher level language, just tell the computer what to do, and it would figure out how to do it. 1970s were the birth of what is called the AI winter. Why is it called AI winter? That's because the first wave of optimism kind of died out, and also research funding greatly died out during that period. And there is one story that's told to illustrate this, which is most likely apocryphal, but nevertheless, it's such a good illustration, I think, of what happened during that time that I want to show you this. So the story goes that there was this big DARPA program manager who was funding this AI research program, and it was demo day, and he came to check out the system, and it was a natural language translation system. And it was the 70s, of course, so the language they were most interested in at the time was Russian. But the guy didn't speak Russian, so the way he wanted to test the system for the demo was put in an English sentence, have it translated to Russian, and then back to English, and see how it compared with the original sentence. Yeah? So this was the original sentence to Russian and back to English, right? So notice those words in color. So the story goes that the sentence came back, "The vodka is good, but the meat is rotten," right? And that was a great demonstration of the failures of the system, actually, and so a lot of funding died out. So whether or not this is true, it is a pretty good illustration of the kind of things that for the longest time natural language processing systems have had a lot of difficulty with. And in fact, perhaps one reason they were having those difficulties can really be boiled down to 6 words. And these 6 words, if you had gone back to the 50s and told the founders of that conference, it would have completely astonished them. But if they had believed you and acted on that, it would have really changed the course of AI and of the world, I think. And those 6 words are now well understood and completely internalized by the software engineering community and in particular the machine learning community. But it's simply this: the fact that intelligence arises from data, not from code. Having data sets that contain a lot of knowledge that you can train your machines on is far more important than having sophisticated code in which you try to program the intelligence in to the machine. So this is something that's well understood today, wasn't quite at the time. So when you go to from the 70s to the 80s, we see people sort of maybe coming around to this view a little bit that you had to get away from these, what's been called physics envy. A system that's going to be really simple, like we hope the physical laws of the universe are, that's going to encode intelligence that's going to be both very general as well as very sophisticated and perhaps human equivalent. But the way in which in the 80s people tried to move away from that was to program in giant sets of rules into the system, and that was called expert systems. So expert systems was really the big obsession during the 80s. And from what I understand, these things were commercially successful. They were used by banks and other companies. It saved them a lot of money. But in terms of the intellectual line of research, it once again proved to be a dead end. Encoding a lot of rules by human experts into the system, for example, for medical diagnoses or for other applications, which are some of the things that these things were used for, didn't really turn out to be the way to do things going forward. So what we have today as machine learning really took root in the 90s. And now, to be clear, the science had been developing, well before the 90s. But when it really got its legs and started to be used in practice was during the 90s. And that sort of went hand in hand with the birth of the World Wide Web. From what I understand, at least, the web and using the freely available data on the web to do a variety of things, including whether it's double-click predicting which ads to show to people, or a variety of other machine learning tasks online. This is where machine learning really found its first set of practical applications that touched a lot of people. So one can ask the question, why was it the web? Why was it not in medical diagnosis or any of the variety of other tasks for which we've gradually started to use it today? And I don't know the answer to this. I can only speculate. But here are some possible reasons, right? Here are some things that were different about the web context compared to a lot of other contexts. One is that it was unregulated. If you want to use a machine learning-based medical diagnosis system, it's not going to be easy because obviously you have to first convince the human experts, that is doctors, to use the system. But also you have to worry about who has the legal responsibility, the accountability for the use of that system. And those are, of course, issues that we've started to worry about today, which is why we have this whole field, and which is why I'm giving this talk. But initially, at least in the web context, you didn't have to worry about those things. Again, same thing with self-driving cars. What if you put a learning system in a car? Who has responsibility if it malfunctions and the car crashes? There were not many slow-moving incumbents to worry about. Easy availability of labeled data online, obviously, right? So to be clear, I mean, the data existed. These large banks and retail chains and so on, well before the 90s, had their CRM systems and centralized databases where they collected all consumer data, and they were doing data analytics on it, but they were not necessarily going to share it, for example, with a couple of Stanford grad students who were the people that founded Google, and so it wasn't quite as easy to obtain. So if you think about it from the lens of startups and disruption, those established industries were much harder for this new technology to penetrate than a completely new and unregulated domain with a new set of applications. So that's kind of my hunch for why that happened. Another thing is that relatively simple techniques work for a lot of things you want to do on the web, as opposed to, let's say you want to look at, medical images and diagnose cancer or whatever. Then, that technology is rapidly advancing today, but that's because of advances in computer vision and deep learning and so on, which is much more sophisticated than what has been typically applied on the web in a lot of cases. So I think it was probably a conjunction of all those things that enabled machine learning to take root. Now, let me tell you a story about machine learning to illustrate a point that I want to make. And the story is apparently this. It turned out that someone did a study that said, if you're looking at small businesses and you have a lot of data about the small business, and you want to predict, if you're a bank giving a loan to that small business, whether or not it's going to go under. So they developed a machine learning system for that. It worked pretty well. And then they tried to analyze that system and try to see what was it in there among the variety of different features that they put into it that was causing it to perform so well. And they found out, more than anything else, the thing that best predicted whether or not the small business was going to succeed or fail, unlike what we might intuitively imagine, it turned out to be the consumer behavior of the owner of the small business. Right? It's not the performance of the business itself, apparently, but more what the owner does as a consumer, whether they pay their credit card bills on time on their personal credit card. And another feature was how often people go to the dentist, apparently. It has a lot of explanatory power because it separates people who plan their health and also their finances, which go together, from people who don't. And so this kind of story is very typical of machine learning. These are at least examples that I can sort of verbalize and share with you. There are many other examples where a system produces some output, it performs really well, but you don't necessarily know what is even the feature that caused it to perform so well. It might not be a single feature. It might be a collection of 100 features that you put into it, right? So these machine learning systems are inscrutable. You don't know ahead of time how many features or which features you might have to put into it to get it to give you the performance that you want. So the bottom line there is really that machine learning is hungry for data, right? And this cannot be emphasized strongly enough. I can tell you some anecdotes, but really, the industry has really, really internalized this, and that's why you see the web domain in particular, but a lot of other emerging technology spaces being so hungry for people's personal data, because with machine learning systems, it's really hard to know ahead of time the boundaries of what data you might want and will be useful to you for the predictive tasks that you want to run. And that story, by the way, Solon, do you remember the name of that book that we took this from? Predictive analytics. There you go. So anyway, that story is from that book. Today machine learning has just completely come to dominate artificial intelligence. It's not AI is not only machine learning, but it is, I think, mostly machine learning. Not necessarily just in terms of what's being applied out there today, but especially if you look at the set of scientific ideas which people think really have a future, and what things are going in terms of what things are going to look like in the future. Especially with emerging ideas like deep learning, it seems like machine learning is only going to be, if anything, an even bigger part of artificial intelligence. So I'll make a sort of a one-slide detour/rant before coming back to the theme of my talk, which is I want to consider the fact that AI is mostly machine learning and use that to say, what is it that we should worry about when we're worrying about artificial intelligence, right? So obviously we want to worry about the things that machine learning is doing or it's going to do. So we want to worry about jobs being automated away by machine learning. That's very much a legitimate worry. We want to worry about data-driven discrimination, which is mostly a big part of what I'm concerned about today. We want to worry about killer robots, because if you have robots that have these capabilities to perceive their world and act autonomously, then obviously that's a huge problem in terms of accountability. On the other hand, there have been a lot of worries expressed recently about artificial intelligence in the traditional sci-fi sense of sentience and the machine waking up one day and deciding to run amok. And so even some writing and research in response to that about how do you put AI in a sandbox and keep it safe so that it doesn't escape and so on. So when I look at that, based on what we know scientifically, what we can predict rigorously about the future of AI, that seems to verge on the silly to me. I might yet change my mind, but so far I have not found a lot of scientific basis for that whole line of worry and research. But I think these categories are all things that we can start addressing today, and there's even a lot of empirical work to do in addressing them. So that's what I want to come to now. In the beginning, I said there has been an explosion of interest from a variety of groups, media and ethics scholars and legal scholars and so on. But when I say how should we react, what I'm interested in is how should computer scientists react? What can technologists do to do their part of addressing the problem of having some oversight on machine learning? Okay, so the current approach to this, in terms of the volume of papers being written in computer science, basically boils down to one sentence, and that is deprive the machines of data. Right? So a lot of this work comes down to, okay, let's look at what the system was supposed to be doing, whether it's serving you behavioral ads, whatever else it's doing. Can we find a way to architect that system so that it still does that same computation, but without seeing the data in plain text? Can we achieve it in some sort of encrypted form? So crypto is often a very huge part of the story. And if you do a Google Scholar search for privacy preserving, in quotes, that's the best way to find these papers. That's the term that most of them use. And this top paper I don't think is as cryptographic, but a lot of the search results that you're going to find are cryptographic. And again, I want to emphasize that I'm not criticizing other people here. I've certainly worked on this myself. This is, again, co-authored with Solon, privacy preserving targeted advertising. I have a few of these papers. And it's a very popular line of research. Can we architect an online behavioral advertising system so that the data actually never leaves your browser? The server only sees some form of the data that's not necessarily in plain text, or the computation happens on your device and so on. But I've also taken a very critical look at this line of research, the answer to privacy being let's do things cryptographically so that the service provider doesn't have to see the plain text. I can point you to that paper. It's called What Happened to the Crypto Dream. But if I can tell you in one sentence what this entire line of work, and I'm really talking about thousands of papers here, so it's a little bit of a generalization to say one sentence about trying to refute all of them, but this is more or less true to a first approximation. So all of these have the point of view of depriving, again, the service provider of the data, but still allowing them to do the computation that they want. But that's not how things work in practice. Exactly as I showed you from that small business example, you don't know ahead of time what data you'll want, and if you collect a certain piece of data, you don't know ahead of time what computations you'll want to use it for. So this very model is just antithetical to the way that these service providers want to operate. They want the data. That's a first-rate goal, and they see providing a service to you as almost just an inducement for you to give up that data. So architecting the system in a way so that they can provide the service without seeing the data doesn't make any sense whatsoever from the point of view of their business models. So there have been dozens and dozens of these papers, whatever domain you want, targeted advertising, vehicular privacy, genetic privacy, and so on. And in many of these cases, I've talked to these providers and sat down with them and tried to understand the requirements, and it just doesn't seem like this crypto-based model for privacy is a fit with the business realities of practice. There are some exceptions, a small number of exceptions, of course. Google's rapport system is something that I'll encourage you to look at. This is in Chrome browsers, every Chrome browser. So there have been exceptions. Rapport, though, is not crypto-based. But when you talk about these cryptographic ways of limiting service provider access to data, you really run into strong practical limitations. Okay. But I want to connect this back to history, and I want to make perhaps a bold claim, which is that the computer science obsession of the view of crypto as a response to all or most privacy worries is in fact an accident of history. And I want to claim that things could easily have evolved differently. And I want to use that to motivate what I think a research agenda should be for computer scientists. So I want you to imagine this world. I want you to imagine a world where AI researchers had recognized maybe 2 decades earlier that data was the key to intelligence and not code, right? And the data was widely available. Again, these banking systems, large retailers, a variety of medical systems, they did have the data. They just didn't think to make use of it in the way that we now know. So they had realized that. And also, I want you to imagine no internet and no consumer computing devices. The banks, and others had these big mainframes and other computing devices. All of those existed, in the 60s and 70s, but the microcomputer revolution hadn't yet happened, and the internet was still a research project and wasn't. The World Wide Web hadn't been born and wasn't on all of your mobile devices. So I want you to imagine a world without all of that, and that I claim would also have been a world without public key cryptography. Why? Any guesses? Pardon me? Yeah, exactly. Yeah, so public key cryptography, if you look at Diffie and Hellman's original paper or some other early works during the period, developed explicitly as a response to the internet and for this need to communicate over the wire with no pre-established identities, right? So that would have been an interesting alternate world where large bodies of data very much would exist. Machine learning would exist. You would have a lot of the privacy worries that you do now. And what I want to emphasize is how much of the things we're talking about today would still exist in this world, even though we think of it inherently as a property of this world with the internet and with consumer devices. That's not actually true. If you look at this story, for example, that many of you, or most of you have probably seen, how Target figured out that a teenage girl was pregnant before her dad did. Now, this is data that Target collected using shoppers' in-store activity. And they were collecting and aggregating that data for decades. And they ran machine learning on it, which I claim could have easily developed well before any of these other technologies. And then they physically mailed a targeted advertisement to her home. Right? So all of the components of that would very much exist in this alternate world. And many of the other things we talk about today. So I want to quickly ask, what would be some interesting technological questions to ask in this alternate world? And I'm going to use that to argue all of those are understudied in our current world because crypto has just seduced and dominated the intellectual bandwidth of computer scientists who think about these questions of data and privacy and algorithms. And I want to say these are things that we should be doing more research on. Make sense? Okay. So one obvious first step in this world would be to examine the limits of inference, right? And there's some research on this going on right now. It's in I would say a bit of a nascent stage, and there are some issues with it. It overclaims certain things and it doesn't address certain other questions. Let me give you one example of a paper. This is called "Private Traits and Attributes Are Predictable from Digital Records of Human Behavior," perhaps better known to some people as the curly fries study, the one that said people's intelligence is predictable from their Facebook likes, including people who like curly fries are more likely to be intelligent. Does that story sound familiar at all? It was in Colbert and stuff. So one of the likes that they said was most predictive of intelligence was the Colbert Report. So you have easy, free way to get on the Colbert Report. There was a lot of news attention given to this paper, and it's good science. I'm not arguing with it. They showed that you can take a record of entire record of a person's Facebook likes and use that to predict a variety of things, religious and political views, sexual orientation, and so on. And in technical terms, they had an AUC of 0.89 or something like that for sexual orientation. These are impressive results, much better than random. But then they went on to make certain claims. And this is from the paper. They had this thing called selected most predictive likes. Apparently, high intelligence is predicted by Godfather, Mozart, and Lord of the Rings, and low intelligence by Sephora, I Love Being a Mom, and Harley Davidson. So this is like built-in virality right here because it just plays into our existing prejudices, right? And so people really liked what this concluded. And it just has this, you can sort of maybe try to imagine why this would be true, but it's not obvious. So it's sort of at the edge of your intuition. But here's the thing. They carefully put this into an appendix. They didn't claim that these results were scientifically valid, and I have a strong suspicion that this whole thing is in fact just bogus. And when they selected the most predictive likes, they didn't correct for a well-known statistical problem of multiple hypothesis testing. I cannot prove this without having the data, but that is my claim. That is my hypothesis. And so in that way, I think this was an overstatement of the results. Machine learning does not, in fact, have this kind of nice property where, there's a few likes that really tell you a lot about that person. It's kind of something that you want to believe, but I don't think that's actually the case. So the point that I want to make with this story is that the current research on machine learning and inference suffers from a lot of bias in reporting of the results and the way in which the reporting is being shaped in order to fit within our prejudices. And I think Solon's in particular done a lot of writing about this, and he can tell you a lot more about this. So that's one problem that's sort of currently hindering the science. But I also want to claim that a lot of important questions are not being addressed. And one example of this is that Paul Ohm and Scott Peppett, among others, have sort of hypothesized that everything predicts everything in the sense that maybe your driving habits are going to predict your FICO score, right, your credit rating, and so on. And they've claimed that for all practical purposes, a variety of these pairs of inferences are true given sufficiently powerful data and algorithms. And implicitly, I think a lot of people are proposing this sort of very powerful statement as a basis for policy. And if we are going to take that unquestioningly as a basis, and things are sort of heading toward that, given the nature of news reporting on these inference studies that come out, that's going to be, I think, very dangerous if we don't carefully examine whether or not the statement is true. And again, my hypothesis is that the statement is not true at all. There are many strong inherent limits to predictability. And those inherent limits, the limits could come from a variety of different ways. It could simply be a limitation of the current data that we have. It could be a limitation of the current state of our algorithms. But also there could be a variety of different types of inherent limitations to the phenomena themselves that we're trying to predict. And we don't currently have an understanding, whenever a study comes out in terms of inference, of where the limits lie, and to the extent that there are errors in our current ability to predict which of these categories they lie in. And we're not able to extrapolate into the future and say, once we have a lot more data, once we continue making improvements to our algorithms, where that ability to infer things is going to go. So right now, the science of talking about these limits is very, very poor. It's something that technologists, computer scientists, machine learning experts can absolutely start doing right now. It's not happening, and that's one area where I think a lot more work needs to be done. Okay. Another whole dimension of research for reasoning about, if we're talking about these black boxes in our society, taking in our personal data and determining our lives, then why not build technology for reverse engineering those machine learning systems? Right? So this is something that I've spoken about repeatedly here. We had basically a whole conference about this that Solon and I co-organized, and Ed and Joanna and others helped to organize. And so I won't go too much into this, but I'll just say a few sentences about there's a great tool. A variety of people are building tools. Let's start with one at Princeton. Nick Feimster and some of his students built a tool called Babel that measures Google search results, or the order of search results for different people in different parts of the world, and uses that to see, to infer things about Google's search algorithm, especially personalization of Google's search algorithm to different people around the world. There's a tool called X-Ray at Columbia that tries to determine input-output relationships, such as the emails that you put into your Gmail and the ads that come out. There's a tool called the Ad Fisher at Carnegie Mellon. Again, similar goal. People are trying to, reverse engineer price discrimination in a variety of online systems. So this is, a nascent area of research. It's good. This has come out, all of this has come out in the last couple of years. I'm glad that this is happening. Again, one big limitation here is that all of these study online systems. And I think that's a big problem. They're studying online systems. We're doing some of this work as well. Again, we're studying online systems because that's what's easy to study. But I think a lot of the interesting phenomena happen either in the offline world or at the boundary of the online and offline world. So again, a lot of limitations in this whole area of research. A third thing you can say is, okay, let's say there is a service provider who is very attuned to these concerns about their machine learning systems and want to do it right. What can you tell them? What can you tell them about designing from the ground up for fairness, for transparency, and for accountability? Right. There's a bunch of research on this. I'll just quickly mention 3 different papers, but I don't want to make it look like these are the only ones. So there's one paper on interpretable machine learning by Ben Latham and Cynthia Rudin at MIT and some others. So here's an example of what they say. They say you can take a medical diagnosis system and you can that doctors are currently using today, and you can greatly improve its performance using machine learning while still coming up with a set of rules that's easy enough for doctors to understand. Yeah, so this makes sense, right? So this is predicting stroke risk. They've compared the performance of this system called Bayesian rule sets, I think is what they call it, to what doctors are currently using. And they've showed that the performance has improved without hurting the interpretability or comprehensibility of the machine learning system. And if a doctor, for whatever reason, wants to overwrite one of these rules for a particular patient, they can certainly use their judgment to do that. So the human is still in control of the system. This is a good first step. But what has not happened here, so what the authors have managed to do here is come up ultimately with a set of rules that is interpretable. But that might not always be the case. In many cases, the system that's going to have the best performance inherently uses hundreds of features as opposed to the half dozen or so that are being used here. So that is a much harder problem, a more important problem that, as far as I know, hasn't been tackled at all. So how do you take a system, acknowledge its inherent complexity, and allow the human to understand as much as possible about the behavior of that system? So again, first steps have been made, but there are many limitations. There's a related line of work on interactive machine learning instead of interpretable machine learning, where the human and the machine work in concert, where the human in real time labels some examples and the machine learns from them and tells the human which further examples need to be labeled, and they together build a machine learning system. So that's another threat. There is fairness through awareness. This is Cynthia Dwork, Moritz Hart, and others. So here they're addressing a different problem. It's not the transparency of the machine learning algorithm, but the fairness of the machine learning algorithm. In particular, the idea that it might, a learning algorithm might have disparate impacts on different groups of people. Let's say an insurance premium setting algorithm or whatever could have different impacts on different gender or racial categories in a way that we find unacceptable. So what they say is fairness through blindness doesn't work. if your goal is that certain groups of people should not be treated differently, and so you simply decide to remove those variables as inputs to a machine learning system, it's going to do very little to help you, because we're talking about systems that have hundreds or thousands of data points, features on a particular individual. So even if you remove those particular variables, it's trivial to predict them using the other variables. And even if the designers of the system don't explicitly set about doing this, machine learning can automatically infer those variables or bypass the need for those variables in the process of determining the final output, and thereby have exactly the same behavior that you're trying to prevent. So their approach to this is in 2 steps. You want to define what they call a similarity measure between individuals that defines how similar individuals should be treated similarly, instead of defining how individuals should not be treated differently. And then they have a way to maximize utility subject to the fairness constraint that was determined in step 1. At this stage, again, this is still theoretical research. People haven't managed to translate this theoretical framework into an actual similarity measure for any practical domain. So again, first steps have been made, but a lot of work remains to be done. I asked you to imagine this world without crypto, without public key crypto in particular, but actually we do have it, and and we can make use of it, I think, in worthwhile ways. So this is work by Josh and Ed. Josh, are there others involved in it?
No, it's just
yeah. And this is a very neat example from their paper. What they say is you can have a framework for accountable algorithms, and they apply it to this example of a tax authority that has an auditing algorithm for determining which individuals have suspicious tax returns and should be audited. Obviously, you want some accountability over that algorithm, because it can cause a lot of trouble if you're audited for no good reason. And so what you can achieve using crypto is the authority can commit to the secret algorithm in advance, can publish something that acts as a commitment to the particular algorithm they're using. And as they carry out their audits, in each case, they can assert that the algorithm that they committed to, without in fact revealing the algorithm, and that's where crypto comes in, they can assert that the correct algorithm was applied to the individual taxpayer's data correctly to come up with the yes or no output for each individual. And finally, whenever necessary, they can reveal that secret algorithm to an oversight body, and only to the oversight body, while still making sure that this is the same algorithm that was committed to in advance, and also making sure that step 2 was executed correctly. So crypto allows you to do certain things that are very cool and unintuitive. So this is not a use of crypto for privacy that I criticized earlier. It's a use of crypto for accountability. I like this way to use crypto for algorithmic accountability more than saying, let's make sure nobody has access to our data. Because if you wanted to do things in such a way that the IRS doesn't actually see your income and other inputs to your tax return, I don't think that's going to result in a very practical system. OK, so hopefully what I've convinced you of is that the algorithmic society that we're in, the particular form that it's taken, computer science has taken a sort of a meandering route there. And things could have gone in a different way, or at least have happened at different points in time. And because of the way that technology evolved, computer science came up with a particular response to it that was very focused on crypto. And now there's been a gradual realization that we want certain other kinds of responses, accountability and transparency for designing things from the ground up, for examining the limits of some of these algorithms and inference, as well as for reverse engineering these existing systems. So while all this is happening, there's one key thing that's, I think, really missing from the computer science community, which is the community building around this hasn't happened yet. And again, I'll point out a few nascent efforts in this direction. So this was the conference/workshop that I referred to that we ran last year that brought together a bunch of people who want to sort of reverse engineer these black boxes. This is, again, something that Solon co-organized. This is Fairness, Accountability, and Transparency in Machine Learning. This is Data Transparency Lab. The person leading this, I think, is Nikos Loteris in Spain. And they've also come out with a grants program recently. And this is an MIT workshop on accountability, et cetera. So all of these are nascent efforts to bring these groups of people together. They've been sort of one-time ad hoc, and they don't look at the whole vision of the problem that I've described. In many cases, they're subsets of that problem. But that's OK. Again, that's a start. But for those of you who are not in CS academia, there's an important limiting factor to how research can happen, which is that if you don't have a way to get credit for the work you're doing in terms of publications, that work is not really going to happen, right? And that right now is a huge impediment in the computer science community for doing this work. And the reason for that is while people are finding some ways to be scrappy and meet with each other using these impromptu workshops, there's not yet an identity within computer science of the kind of work that I've talked about today. It's not an acknowledged and existing community. There's no regular meeting of that community. That's an important point. And the other important point is that there is no single venue for publishing a lot of this work that I've talked about, even though there's a lot of cohesion to this work, right? How do we respond to algorithmic society? That's the defining question of this work. And yet, if you look at where it's being published in computer security venues, it's being published in computer systems venues and machine learning venues, obviously, and actually a variety of others, at least 5 or 6 different venues. And each time, the authors are having to convince their respective communities that algorithmic society is a real thing, that computer scientists need to do something about it, and here's something you want to do about it that can make things better. Right? And the work that they're publishing is generally not relevant to the rest of, say, what the computer security community is doing. It borrows techniques from all of these different disciplines. When I talk about reverse engineering, certainly my expertise in computer security really is useful there in having this sort of adversarial point of view and determining how things can go wrong and how to reverse engineer the system and so on. And obviously machine learning expertise is essential. Obviously human-computer interface expertise is essential, but it doesn't mean that you want to publish this work that has a common theme in like 6 different communities, given that these people all have a lot more to say to each other than to these other different disciplines. So I don't quite know how to solve this problem, so I just sort of wanted to end with this as on a hopeful note, because a lot of this grassroots effort is happening. But at the same time, the key problem of being able to have regular meetings and publish these papers and build off of each other is not happening. In a lot of these cases, the authors of these papers are not aware of each other's work and reinvent a lot of what's already happened because it's in so many different communities. So I wanted to end on that note that computer science has a lot to offer here. If you look at legal scholars, for example, PLSC, the Privacy Law Scholars Conference, is one venue where a lot of the sort of the legal responses to many of the questions discussed here are being responded to. And I've been to PLSC the last several years, and it's been wonderful to see that emerge. So a similar identity has not emerged in computer science, and I think that's an important problem that needs to be solved. Typically, it's for, I think, more senior people with a lot of authority in the community to solve. Just to give you one example, economics and computer security were similarly 2 disparate areas that people realized needed to be brought together, and Ross Anderson, almost as an individual, made it happen, I think around 2001. Josh, you might know this better, by starting the workshop on the economics of information security. So perhaps something like that needs to happen for algorithmic society, and I thought I'd end on that note. Thank you.